Okay, so these gas density problems, they're kind of long. They take a lot of steps, most of them. So we have to remember our old formula for density, our D equals M over V, because we use that to sub in for some things sometimes. And we also have this formula, which is probably our most useful. So we can use both of these equations. In these problems. And in fact, we can take them and we can arrange them. Well, first let's put this out here. Out to the side, there's this symbol. It's either a double M or a single M. And when you see that, that's representing molar mass. Sometimes that's subbed in as well. So we can take these and we can arrange them to have similar units. We want to think about the units of moles per whatever volume I'm dealing with. Normally it's liters, but on occasion it might be something else. If I rearrange my ideal gas law equation, I can set P over RT equal to N over V. Now think about this. If I take my number of moles times my molar mass, that was really crooked, then I've got grams per mole. So my moles will cancel out. That'll get rid of this. It will get rid of my moles, and it'll leave me in grams per unit of whatever my volume is. Does that make sense? So this is another valid equation to work through all of those things. Oops. So then I could possibly take both of those equations, and due to the units, I can say that density then could be equal to the number of moles times the molar mass over volume, which is equal to pressure times molar mass over my ideal gas constant times temperature. So it puts the whole thing together. And what this does is, let's say this tells us the density of a gas depends on its pressure, its molar mass, and its temperature. So it's affected by all three of those things. And I can draw some assumptions from that, or I can make some statements by thinking about that. I could say the higher the molar mass and the pressure, the denser the gas. I could simply just say the higher the molar mass, the denser the gas, because remember, if we're isolating that molar mass, then my other things for all, if I was talking about 4 different gases, my volume would be the same for all of them. So we're isolating one thing to think about, really. I could also say the higher the temperature, with increasing temperature, what do you think happens to the density of a gas? If I increase the temperature of a gas, what does it do? What?
It's smaller. At least like
It expands, right? Yeah, so that's not getting smaller. That's taking up more space. If I take up more space, what happens to my volume, Seneca? Up or down? If I take up more space. If my gas is heated and it expands, it takes up more space. What's true about the volume of the gas? Okay, so when the temperature goes up, the volume increases, which does what to the density? What'd you say, Kira? To begin with.
well, it makes it bigger, but it makes.
What does it do to the density? Now my volume got bigger. Did I change my mass? No, so I'm dividing the same number, the same M, by a bigger V. So what happens to my D?
It's smaller.
Yeah, it gets smaller. The density decreases. Okay, so let's see, what else can we say? We can say that we know that gases form what kind of mixtures? Yes. So even though they're forming a homogeneous mixture, we have to remember that even so, the less dense gas will lie above all the others. I'm going to say in the mixture so it makes sense. So even though I know I have multiple in there, the least dense gas is going to be the one that lies on the top of the mixture. So let's look at these two. So I have those three gases. Which one of them would lie on the top of a mixture? If I think about this, in air I could find all of these things. These two are the largest components of air. It's going to be the most of those. But of the three, which are going to be towards the top, and which is going to be towards the bottom? If I'm talking about the way they would layer. How are you going to figure that out? Yeah, so figure it out. Hello? I'm sorry. No, she's not here. Okay, thank you. Okay, what's the molar mass of carbon dioxide? Seneca? It is. N2, nitrogen gas. What's the molar mass, Carly?
1 grams.
And O2 is what, Kira? Coal? 32. Always forget I've got two of you guys. Okay, so who's going to sit on top? Nitrogen, followed by oxygen, followed by the carbon dioxide. Well, because these two are the largest components of air, if I calculate the mass of air, it's going to be closer to these guys. But this whole logic right here explains a lot of things. It explains, have you seen dry ice before? Yeah. It explains that whole phenomena. How when it evaporates, it causes water to condense in the air, and then that water is carried down by with the heavier CO2 gas, which is why when you have that, you can kind of watch that gas from dry ice fall. That's how it works. It's the same way a fire extinguisher works. A CO2 fire extinguisher, you pull that, you spray it towards the flames, that you see the foam, but some of that foam becomes gas as well, and it moves down and it envelopes those flames. All that's based on the molar mass of carbon dioxide and how it behaves in air.
But there's no like straight layers, right? Because they can still.
Right, right. There's some intermingling because they're all, think about it, they're all moving.
Right, they're just generally
Yeah.
more concentrated. in
Yes.
different layers.
So if I have equal molar masses of two gases at the same temperature, but different pressures, let me see how to ask you a question about this. Which gas will be less dense? How would you figure that out? What would you have to do? What'd you say, Kira? The one with the higher pressure will be less dense? More dense. Why? Okay. So when you say more pressure, what if I have more pressure, what does that do? Like, think about a picture. What does that do to the gas? It what?
Smaller volume.
Yeah, it squishes it, right? So that's logical. That makes sense. If I have two gases, same molar mass, but not the same temperature, different temperatures, what's going to happen to the gas with the higher temperature? Less or more dense than the other one? Less dense, because higher temperature, it spreads out. Same principle we talked about. That's how lift in a hot air balloon works. You know, they always have the little flame in the center. That's to heat the gas inside the balloon, and then it will rise because it's less dense than the air that surrounds it. Because there's nothing special inside that hot air balloon but air, heated air. So, maybe we should. And then maybe let's go back to wherever I had that. And just off to the side, let's write dry ice. What's the other thing? Oh, what else did I talk about? Oh, fire extinguisher. So you've got a couple of examples. The what we just talked about and the difference in temperature in gases has a lot to do with our weather. Hey, they've been checking on me. I just got a call about you. And like situations like we had last night, which I think that was way overblown. I don't think it turned out to be anything like they were talking about. But you can almost feel the change in pressure and temperature and see what it does to the sky. And that's all based on the gases in the atmosphere, why those things work that way. Okay, so then we can say, using the density of gases equation, we can rearrange it to solve for molar mass. We just talked about that. When I do that, I get a formula that looks like this. Molar mass is equal to density times the ideal gas constant times temperature over pressure. And you can use, and you'll have to in problems, you can use an experimentally measured density of a gas to determine molar mass. There's probably even a table, I haven't looked, but there's probably even a table at the back of your book that gives density of gases at a specific temperature at STP. Okay, so I need to grab one of those papers. Oh, Brooke, you need one of these so you don't have to write these questions out. Some of them are kind of long. Let's look at this first question on here. Take a minute and read it, which is what I need to do. A large flask initially. Okay, so I'm just going to work through this in a logical way so that you maybe have a little bit of a path to follow when you come along these really long questions. So the first thing you want to do always is to make any necessary conversions. So immediately I see we have a pressure conversion we need to make, and we have a temperature conversion we need to make. So get your calculators out, take a minute and do that. Oh, that's 7:35. Seneca, what's the pressure? 0.9 what? 6? Okay. 9.6. I'm going to carry it out one more. 9.6. Did you get 9.67? Yeah, okay. All right, so that's a good place to start. Then we'll look to the problem and we'll see what we need to do next. So we're going to have to find several different things. And it makes sense to me because we have an empty and then we fill it with water and we've got a couple different masses going on. I'm going to start by finding the mass of the water because I have to know that in order to find out some things about the gas. I can't find out how much gas I have if I don't know about the water. So I need to take the mass of the full flask minus the mass of the empty flask and see what that equals. So the full flask was 1,067.90 grams minus my empty flask is 134.567 grams. So see what that is. So that equals my grams of water. Now I also gave you some information here about what the density of water was at that temperature. So the density of water will allow me to find out how much water I actually had. So the next step I want to do is I want to find the volume of the H2O. So I'm going to use D equals M over V. So I've got the 0.997 grams per milliliter is equal to M over, no, is equal to 933.3, that's what we have, grams over V. So solve for your V. And I get 930.5 milliliters, which I want to make into liters, 0.9, I'm going to call it 0.93, is that right? 933.3, I think I just did that wrong. Yeah, this should be 936.1. 0.936 is what I'm going to use, liters. I just typed in the wrong number. Type that in, make sure I did it right. Make sure I've got the right, got it? Okay. Okay, so now I know everything I need to know about my water. The next thing I would want to do would be to, let's find the mass of the gas, because we have to know that. What step am I on here? 4. So when I want to find the mass of the gas, I have to take the difference between the filled flask and the empty flask. So I had, where's that? 137.456 grams minus, shoot, I lost it, 134.567 grams. So 2.889 grams is the mass of the gas, which I'm just going to make 2.89. So now, we now know the mass of the gas and its volume, because we can use the volume of the container that the water was in, right? Does that make sense? Because the gas is going to fill the container. And we can calculate the density of the gas. So we've got D equals M over V. So that is equal to the 2.89 divided by 0.936, which is something, or 3 point something. I'm going to call it 3.1. And that is grams per liter. So we've got an important piece here. We know the density, whoops, and because we know the density, now we can use that formula, finally. We're going to use our density gas molar mass formula to find molar mass. So I'm going to use Molar mass is equal to density times the ideal gas constant times temperature divided by pressure times volume. So plug in everything you know. I already forgot what the density was, 3.1. Temperature was 304 over, I don't, it was 0.986 or something like that. 0.967. And the volume was we don't need this here, people. So, now we can do the math. So I can say the molar mass of the gas is equal to 79.97, so I'm going to say 80 grams per mole. So it's a lot of steps. They're not all that many steps. I would get that card out that you have formulas on, and I would put those couple formulas on that we just put in your notes, like this one especially, because that's a really straightforward formula. Sometimes your problems will be a lot more straightforward than the one you just had.
If you don't have a variable like the volume, do you just get rid of it?
No, that shouldn't have been, I wrote that and I shouldn't have to begin with. It's not supposed to be there. This is your formula. M equals dRT over P. Because when we bring the density in, we've already taken care of the volume. And I was just thinking about the old PV equals nRT when I was writing. Okay, so I want to show you one more thing. And this is a problem. We kind of did this yesterday, but we'll put a little bit in your notes about it. Actually, let's take a break from notes for a minute. Let's break and do, I think it's number 52 that's the one that's density in your book. So get together with a partner, work through 52. When you get an answer, let me check it, and then we'll come back and we'll pick up with this stuff. That way you've done that problem before I give you more.